Welcome to homework.
Okay, so problem number 39 states that in section 40.5, it is shown that for the ground level of a harmonic oscillator, delta x delta p is equal to h bar over 2. So this is the uncertainty principle. So it says, do a similar analysis for an excited level that has a quantum number n. How does the uncertainty product delta x delta p depend on this quantum number? So let's start with equation 40.46 from the book, which is the energy levels of a harmonic oscillator. E sub n is equal to n plus 1/2 h bar omega. Let me fix this. One half h bar omega. And so also for a classical harmonic oscillator, the potential energy is given by 1/2 k prime a squared. We'll use a squared instead of x squared. So where a is the amplitude of displacement. And omega is the frequency. And then K prime is the spring force. That's the restoring force, basically. So now at the classical turning points, the kinetic energy of the system of the particle is 0. So the total energy is equal to the potential energy. So we can use that and state that n plus 1/2 h bar omega is equal to 1/2 k prime a squared. And we can solve for a, where a is equal to the square root of 2n plus 1 times h bar omega over k prime. So now, in order to so this will give us the position. So A is your displacement, your amplitude, which is basically your delta x, your position, your x. Now, now we need to get the momentum. So in order to get the momentum, we need to know the velocity. So we can also use the fact that in a harmonic oscillator, at the the central point, at where the displacement is 0, the kinetic energy is maximum. So there's no potential energy, and E sub n is equal to kinetic energy. So we can use that the same way. N plus 1/2 h bar omega is equal to 1/2 mv max squared. So this is the maximum kinetic energy of the particle in a harmonic oscillator. So now we can solve for V and say get V is equal to the square root of 2n plus 1 h bar omega over m. So now the momentum P max is equal to m v max, which is just equal to m times the square root of 2n plus 1 h bar omega over m, which is equal to the square root of 2n plus 1 m h bar omega, because that cancels out with one of these. When you bring it in, it becomes m squared. All right, so now that gives you your maximum momentum. So now we're given also in the book, and this kind of comes about from working out the standard deviation, the variance of your momentum and position operators. You get, you can say delta x is equal to a over the square root of 2, and delta p is equal to p max over the square root of 2. So now what we want to do is find the, multiply these together to get the product let's see, should I create? I'm going to create another page for that to make it a little easier. So we get A over the square root of 2 times P max over the square root of 2 is equal to 1/2 times A, which is the square root of 2n plus 1 h bar omega over k prime times the square root of 2n plus 1 m h bar omega. Okay, so we can bring the m and everything else comes out of the root. So this is equal to 2n plus 1 h bar omega over 2 times the square root of m over k prime, which is just, so this is just 1 over omega, because omega, so if we remember, omega is equal to the square root of k prime over m, so we can plug that in, say delta x delta p is equal to 1/2 times 2n plus 1 h bar omega over omega. These cancel out, so you get 1/2 2n plus 1 h bar. So bring in the 1/2, which is equal to n plus 1/2 h bar. Or so to keep it in the form of the uncertainty principle, so standard uncertainty principle, delta x delta p is equal to h bar. That's supposed to be an h. H bar over 2. So, or in terms of higher energy states, delta x delta p is equal to 2n plus 1 h bar over 2. So to answer the question, how does the uncertainty product delta x delta p depend on n? Well, it increases with n. So as n goes up, the uncertainty goes up.